How are you all? Good, wonderful. I'm glad to see you today. All right. Anybody have anything they want to share? Ellie, are you just waving? All right. Anybody have any questions? All right. Let's dig right into class then. We have a lot to cover today. Okay, go ahead, Josiah.
I took me a while. I'm playing piano at my worship team at my youth group tomorrow.
Oh, that's pretty cool. Is that the first time?
Second.
Oh, well, good luck. That's really wonderful.
I am sick.
You have, oh, sorry to hear that, Evan. You better now?
Yeah.
Mostly. Yeah. All right, let's begin. We're going to continue our discussion of the periodic table of the elements. So can everybody see that? Okay, good, good. So, last week we started learning about it. We're going to do a real fast review of what we covered last week, and then we'll finish it up, and then we'll do an activity together. So hopefully you have your periodic table with you, or you can open one in a new window. You will need one for today, for class, in order to participate. So I'm going to move quickly through the review part. So stop me if you need more. All right. So a couple of jokes first. How can you keep from losing an electron? Well, how can you keep an atom from losing an electron? That should say. Josiah.
Keep everything positive.
Oh, that's a good one. That's a good one. But the what I have is keep an eye on it. Eye on it. Why did the white bear dissolve in water? Because it was polar. Remember, polar things dissolve in water. All right. What did the girl say when her friend threw sodium and chloride at her? That's a salt. All right. And what is the best chemistry advice? So here you go, Josiah. Make like a proton and stay positive. best advice in life, right? Make like a proton, stay positive. All right, let's do a quick review of the periodic table. So this is a cell. Sometimes it's just called an element. Sometimes it's called a square. They're all basically the same thing. A cell contains the atomic symbol. In this case, it's H right there. That's the symbol. The name of the element is hydrogen. It contains the atomic number and the atomic weight. Sometimes it'll also tell you what state of matter it is at room temperature, and it will have the valence electrons in it as well. Now, different periodic tables are going to have different content in them, but that's standard, what we see right there. So what is the atomic number of carbon? Mel?
6.
6. Excellent. And what does the atomic number tell us? Josiah?
The number of protons.
The number of protons. Right, right. So which two elements have the same number of protons? That's a trick question. Josiah?
None, because everything
None.
has a different amount.
Right. No two elements have the same number of protons. What happens if carbon gains a proton? Mel?
It becomes nitrogen.
Yeah, it's no longer carbon, right? If it gains or loses a proton, any element, it becomes a different element altogether. Now, atomic mass, that tells us the mass of the protons and neutrons. Remember, electrons are so tiny that we don't even count electrons when we're figuring out the atomic mass number of something. So this is helium. It has 2 protons. The atomic mass is 4.003. How can it be a fraction? If we're adding together protons and neutrons and there's 2 of each, why isn't it just plain 4? Josiah.
Because neutrons are just a tiny bit heavier than protons.
Well, you're right, but basically what we're talking about when we have that, anything that you see in a fraction or decimal like that, it's that we're taking the average, because remember, atoms can form ions. Isotopes. They form isotopes when they either have more or fewer neutrons. So if an element has isotopes, we take the average of all the isotopes. That's when it would have, a different number. So that is the average of that. So the atomic mass refers to, we use the term weight. We use the term weight because weight works when you're on Earth. Weight doesn't work anymore when you get out into space, or certainly on another planet, because they don't have the same amount of gravity. So really mass is a better term, but you can think, when we're talking about things here on Earth, you can think of mass and weight as being approximately the same, close enough. And like we said, an isotope is an atom that has more or fewer neutrons than protons. Now, most atoms have the same number, but some don't. Some atoms have more or less neutrons than protons. Those are called isotopes. So they're still called atoms, but really they're more variants of the atom. They're just the atom with another proton, or another neutron, or one less neutron. So some atoms have more or fewer, more or fewer electrons than protons, and those are called ions. Now, we don't usually call an ion an atom. We'll still call an isotope an atom, but we don't call an ion an atom because it has a charge. Remember, if it gains an electron, it got something negative, so now it has a negative charge. If it loses or gives away an electron, it just gave away a negative, so now it's got a positive charge. So atoms are understood to be electrically neutral, meaning they don't have a charge. Ions do. All right, everybody good with those? Stop me at any point if you need more, if any of this is confusing. All right, so what color, we can divide our elements into metals, nonmetals, and metalloids. On this table, what color are the metals? Zane?
Blue.
You got it. What color are the metalloids? Josiah?
They're the green color.
Nope. Metalloid.
Oh, no, the purple.
Yeah, they're the purple. They're in between. We call them metalloids because they're kind of like metals, but they're not metals. They're also kind of like non-metals, which are the green ones in this picture. So in this one, the green are non-metals, the blue are metals, and the purple are the metalloids. All right, so we've also got these up and down columns in our periodic table. What are those columns called? Josiah?
I think those are groups.
They are. They're called groups. Sometimes they're called families. So how many groups are there on the periodic table? Go ahead, Josiah.
18.
There are 18. So if we counted here, 1, 2, 3, 4, 5, that just says how many columns are there. There would be 18 of them. So if these are groups up and down, what are the rows crossways called? Somebody's got to help Josiah out here. You're making him do all the work. Mel?
Periods.
Those are called periods. How many periods are there on the periodic table? Ella?
7.
There are 7. Right, right. What are these down here? What period are they in? Mel?
6 and 7.
Right. They go in this area right in here. They are 6 and 7. All right. Which are similar with one another? Ones in groups or ones in periods? Josiah?
Groups.
Groups, right. The ones that are in columns with one another, the groups or the family. That's where I think it helps to use the word family, to remember that a group and a family are the same. They have similar characteristics, not identical, but similar to one another. The ones in the periods in the row are very different. The ones way over here are very different from the ones way over on this side. All right. Now, we have these group numbers, our group names. What do we call this group? All except for hydrogen. Hydrogen, remember, is in a category of its own. So what do we call that first red group? Mel?
Alkali.
Those are alkali metals. Very good. All right, so what do we call the next one? The orange one's right there. Matt?
Alkaline earth metals.
Very good. Alkaline earth metals. All right, so now these here in the middle, they're a little tricky. They're called transition elements. So we're going to skip over them. We're not going to spend a lot of time on them for now. We're sticking right now with the ones that are pretty easy to understand. Not that these aren't important. They just have a little different. They don't have the concrete rules like we have for the other ones. So what do we call this next one? Mel?
The boron group.
They're a boron group. It's called that because it's got the B at the top here. So we call them all the boron group. Why is it a different color than the rest of the ones in the boron group? Josiah?
Because boron is a metalloid.
Yes. And all the rest of these are metals. Excellent. All right. What about this group here? What's this one called? Anybody else? Go ahead, Mel.
The carbon group.
The carbon group. How about the next one? Matt?
The nitrogen group.
Nitrogen group. And the next one? Mel?
The oxygen group.
Oxygen group. And the next one? Josiah?
Halogens.
Those are called halogens. They are not the fluorine group. They are called halogens. And what about the last one? The last ones are very noble. They're very special. Matthew?
Noble gases.
They are called the noble gases. All right, now, the bottom of the periodic table contains those two rows. Those two rows are called the lanthanide series and the actinide series. So we didn't have a lot of time to talk about them last week, so I want to just mention them a little bit this time. Remember that they fit in this category here, and they do that so that the table doesn't look like this. If we put them where they go, this is what the periodic table looks like. So we put them here so that it saves space. Now, all of the lanthanides right here, all those lanthanides except for promethium, which is right here, are naturally occurring, and they can be found in like mineral deposits. But, you know, the amount that you find them in varies a lot from one to another. Now, 5 elements in this actinide series are naturally occurring. These 5 right here we find in nature. 5 isotopes of the others are sometimes produced by the decay of uranium. We'll talk about what decay means. Basically, it means breaking down into smaller elements. The rest have been made in a lab. They've been synthetically made. So there's our periodic table. That's the whole thing. Keep in mind now, this would be, hydrogen would be in period 1, this way, and group 1. This one right here would be in group 3 and in period, not 3. This is the first one. 1, 2, 3, 4. All right, so we've got 1, 2, 3, 4, 5, 6, 7 of these periods, and we've got 18 of the different groups. All right, let's talk about these valence electrons. You have to make sure you understand these because they are really important. The valence electrons are the ones that do the interacting with other elements. So they're important because they're in the outer energy level of an atom. They're the ones that are transferred, either sent to another one or accepted from another one or shared whenever atoms bond to other atoms. We say that they are either reactive or non-reactive. So we're going to be describing elements according to their reactivity. So what do we mean when we say reactive? What makes an element reactive? Josiah.
The way it interacts with other elements.
Yes, but what makes it want to react or not react? What is it about the element that makes it want to react with other elements? Mel.
Elec-
The valence electrons.
Yes, yes. So it's an incomplete valence electron level. So remember, the outer level wants to have 8. That's called the octet rule. We want to have 8 in the outer electron shell. If it doesn't have 8, it's not happy. It wants to have 8. So elements that are reactive are ones that don't have 8. And those will easily bond with other elements in order to get 8. And that makes a compound. Now, some elements are only found in nature bonded with other elements. How many valence electrons do atoms want to have? Ella.
8.
Yeah, 8. All except for hydrogen. They want really and helium. They want to have 8 in their very outermost energy level. Now, atoms will keep bonding until they have 8, until that outer valence electron level is complete. So atoms with not very many valence electrons are going to lose them. They'd rather not have any than have less than 8. So they'll lose them. Atoms that have 6 or 7 or 8, they gain electrons during bonding. So what's the name of that rule? I just said it. Matthew.
The octet rule, I believe.
Very good. Sometimes called the rule of octet, but it's the same thing. So when we say that the ones that don't have very many tend to want to give them up, and the ones that have 7, 8, 7, 6, or 5 want to gain, you get an understanding of why this becomes a little bit complicated in the middle here, right? Because do they want to gain? Do they want to lose? So it has a little bit more to do. It's a little more complicated learning those. All right. So again, atoms that have few valence electrons, the ones over here, are going to lose them. The ones that have 1, these all have 1. These have 2. These have 3 to 12. These are going to have 3 in them. These are going to have 4 in them. 7. Sorry. These are going to have 3, 4, 5, 6, 7. And then these are going to have 8. So if we know how many valence electrons an element has all by itself, we know whether it wants to gain or lose during bonding. And the periodic table tells us that. Now, these transition metals here, these are a little bit, these ones here in the middle, they're a little bit complicated, so we save them for later. But the rest are easy. So how many valence electrons do alkaline metals have? Put your fingers up and show me. How many valence electrons? 1. How about boron? How many valence electrons does the boron group have? 3. What about the oxygen group? How many valence electrons? 6. You got it. Excellent. Now, the noble gases, what makes them noble? All except for helium. Helium's already happy. It has 2, but its outer shell is full because it only has 2 electrons. So it's happy. So all the other noble gases, neon, argon, all the way down, they all already have 8. They're happy atoms. They don't need to give any away. They don't need to get any. They have the 8 that they need. Now, here we have, sorry, don't know why that went so fast. Here we have one unhappy sodium atom. It has only, look at the outside, only 1 valence electron, so it's not happy. Here we have an unhappy chlorine atom. It has 7, but they both want 8. What can you do? Let's say, I've got 7 apples and you've got 1, and neither one of us wants the amount that we have. We both want to have either 8 or 0. You could give your 1 to me, and then I've got 8 and I'm happy, and now you have 0 and you're happy, right? So Sodium does the same thing. It loses one of those electrons. If sodium gives chlorine its electron, they're both going to be happy. Sodium's happy to give away its electron because it has one in its outer shell, and it takes less energy to give it away than it would to gain 7 more to keep that shell full. Chlorine's happy now because it has 8. So everybody's happy. Sodium is happy, chlorine is happy, and people are happy because now we have salt to put on our French fries, right? Sodium chloride. All right, we are going to now do an activity called the alien periodic table. All right, I want you guys to imagine that the inhabitants of another planet have sent a message to Earth that contains information about their periodic table. They want to trade with us. They need to get some elements from us. They want to buy some of our elements for their planet. But we have a couple of problems. Problem number 1 is they only have 30 elements on their home planet. They're completely missing all of those. So this is what they have. These are the elements that they have on their alien periodic table. The second problem that we have is that they don't use the same names we do, and they don't use the same symbols that we do. They don't use O for oxygen and H for hydrogen. They use different names. They use names like Apstrom and Anatom and Bomble and Wobble and Pi and Logon. So we have to figure out what their elements are so that we know what to sell them. Because if what they're asking for is oxygen and we sell them carbon, it's not going to work. So we have to figure it out. So here are the clues that we have about what elements on their table match the elements on our table. Our job is to discover which elements on the periodic table these alien names represent, so we can give them what they want when they place an order. All right, so we're going to now put their elements in the proper place on their periodic table. All right, so here's our clue. The noble gases are Bomble, which is abbreviated BO, Wobble, WO, Gyptum with a J, and Logon, which is an L. Among these noble gases, Wobble has the greatest atomic mass, and Bomble has the least. Logon is lighter than Gyptum. All right, so what goes on the top? What goes right here? Everybody think about it now for a minute. Wobble has the greatest atomic mass. Bomble has the least. Logon is lighter than Gyptum. All right, so what goes on the top? Josiah.
Bomble, because I think that represents helium.
All right, wait for what it represents. We're just going to place them first, but you're absolutely right. Bomble is going to go on the top. It has the least atomic mass. So the higher something is on the periodic table, the less it weighs, the lower its mass number is going to be. The higher ones are down lower on the periodic table. So what goes on the bottom right down here? It's going to be the one with the greatest mass. What is that? Matthew.
Wobble.
Yep. And then what goes right below Bomble? Ella.
Logon.
Logon. And then what goes right below Logon? The last one left. Go ahead, Ella.
Gyptum.
Gyptum. All right. We just figured out their noble gases. These are the stable ones. These are the ones that have a happy filled outer electron shell. All right. Now leaving those in place, Bomble, Logon, Gyptum, and Wobble, the most reactive group of metals are called Extalt, Biu, Chau, and Quaxel. All right. Which group, remember what a group is, a family up and down. Which group on the periodic table has the most reactive elements? Which side of the periodic table is the most reactive? Contains elements that really want to bond. Ella.
Is it metals?
It is. So it's metals, but be a little more specific than that.
Mm,
When you're looking at, you got metals, metalloids, and non-metals. The metals are more reactive in general, not all, but in general. But which group, which family up and down? Josiah.
It's the left side with the alkali.
The farthest is going to be the alkali metals, the farthest down. Yeah, absolutely. All right, so that's going to be the column that we're going to fill in right here. Now, of these metals, Chao has the lowest atomic mass. Now, see, this is separate here because, again, hydrogen is in a category by itself. So we're looking at what is in group 1, period 2. All right, so Chao has the lowest atomic mass. Quoxel is in the same period as Wobble. Biu has a greater atomic mass than Chao, but less than Xtalt. All right, so what is going to go right here in group 1, period 2? It's going to be the alkali metal with the lowest atomic mass. You guys typing your answers in? Yeah, you go. Chao. Very good. Chao. Excellent. All right. Now, what is going to go right here? Yeah, Quoxel is going to go there. Very good. And then our next one is going to be between Quoxel and Chao. What's going to go in period 3, group 1? That's going to be Biu is going to go there. And then finally, what's our last one? What goes right here? That's Xtalt. Xtalt is going to go there. Excellent. All right. We're doing well. Look how much we've got done already. We've solved a lot of this puzzle. Now we'll leave these all in place. And now we will do the next group. So Apstrom, Vulcanian, and Krat are non-metals. Which side of the periodic table are we looking at here now? Non-metals. We're looking at the right side or the left side? Yeah, we're looking at the right side. So over here. So they are non-metals whose atoms typically gain or share 1 electron. So which family are they in? Yeah, they're the halogens. They're going to be this one right here. So we're looking to fill the spaces of Apstrom, Vulcanian, and Krat. Of those 3, Apstrom has the lowest atomic weight of these 3 elements. So where should it go? So let's do group first and then family, or sorry, period next. Yeah, it's going to go on the top. Apstrom is going to go right there on the top. What about Vulcanian? Vulcanian is going to go on the bottom. Yep. And then we are left with Krat right in the middle. Very good. All right. Now, remember that the metalloids are the ones that look like steps. So the metalloids are going to go in the red boxes. Their metalloids are Ernst, HiHo, Terriblum, and Cissus. Cissus. I didn't make these up. I found this game. So Cissus. Now, Cissus is the metalloid with the greatest atomic mass. Where's it going to go? The greatest atomic mass. So tell me the period first, and then, I'm sorry, the family first, then the period. 15, 4, right there. Yep, you got it, James, right there. That's where it's going to go. All right. Ernst is the metalloid with the lowest atomic mass. Where's Ernst going to go? It's going to go 13, group 13, period 2, right there, Ernst. All right, now HiHo and Terriblum are in group 14. So let's find group 14. This is the group 14 right here. Terriblum has more protons than HiHo. So where is HiHo going to go? Do the family first and then the period. Yep, it's going to be 14, 3 right there. All right, now the last one left then is going to be Terriblum. We know that that's right there. Now, Yazur is in the same group as Ernst. and the same period as Hi-Ho. All right, so find it. Same group as Ernst, same period as Hi-Ho. Yazzer touches the zigzag line, but it's a metal and not a metalloid. So it is going to be 13-3 right there. All right. Is anyone completely lost and has no idea what we're doing here? Now's the time. If you're completely lost. All right. So what we're doing is we're just figuring out what we're doing really is we're learning the periods that go this way and the family, group, row, column, whatever goes that way. All right. So let's move on to the next one. Now, the lightest of all elements is Fst. Where does Fst go? 1-1. Yep, it's going to be in group 1, period 1, right there. All right, the heaviest element in all these groups is El Dorado. Where does El Dorado go? 14-5. That's the heaviest that they have. Because remember, farther over to the left and farther up to the top are both lighter than the ones that are farther to the right and farther down. So it's going to be right here is going to be where El Dorado goes. All right, now the element doggone only has 4 protons in its atoms. Where's doggone going to go? Yep, it's going to be 2-2 right here. Period 2, family 2, or group 2. Guys, we're half done. We're more than half done. All right, now Floxit is important in the chemistry of life. It forms compounds made of long chains of atoms. Floxit has 1 more proton than Ernst. Where's Floxit going to go? 14-2, right here. Yep. All right. Rat trap and doadir are metals. That should tell you which side of the periodic table they're on. Remember, we have metals on the left, metalloids in the middle, and then non-metals on the right. So it's going to be over on this side over here. These are the metalloids. So it's going to be over on this side here. So they are metals in the 4th period. Where's our 4th period? This one right here. But rat trap is less reactive than doadir. So what's going to go right here? Rat trap or doadir? Yep, it's going to be rat trap. Exactly. And then that leaves doadir to go right there. Magnificon, Goldie, and Sisyphus are all members of group 15. Goldie has fewer protons than Magnificon. So first we find group 15. Here we go, group 15. We know that Sisyphus is already part of group 15. So we just have to add in Goldie and Magnificon. Where should Goldie go? 15-2 is where Goldie should go. Right here, 15-2. And then Magnificon is going to go right there. We have Magnificon and Goldie. All right, a couple more left. Earp, Oz, and Nuyut all gain 2 electrons when they react. So since they gain 2, where are they going to go? On the right or the left? They want to gain 2 in order to be happy, in order to have 8. So they're going to go on the right or the left? Since they were going to gain 2, they're actually going to go on the right. They're going to go over on this side over here. Remember, these have 8, these have 7, so they gain 1. These have 6, so they need to gain 2. All right, so they are in group or family 16, right? So all of these are going to be right there. Nuyut is the lightest of the 3. It is found as a diatomic molecule and has the same properties as a gas found in Earth's atmosphere. All right, you guys remember what group 16 is on our periodic table? What's it called? Yeah, it is the oxygen group. So where does Nu, which is Nuyut, where does that go? 16-2. You got it. 16-2.
Top.
Yeah, very good. All right, now Oz
It is
has
oxygen.
Oz has a lower atomic number than ERP. So where should ERP go? 16, 4. Anybody disagree with that? Good. That's exactly it. All right. And then finally, we have Oz because we know they all gain 2 electrons when they react. They have 6. They want to have 8. All right. We're almost done. Very little left to go. Now, the element anatom has atoms with a total of 49 electrons. It is the second largest element on the table. Where should it go? $13. It's going to be
In the
group
bottom.
13. Yep, right here, group 13, period 5. Excellent. All right, Zapper and Pi lose 2 electrons when they react. Since they're going to lose 2 when they react, which group are they in? They're alkaline earth. They're in group 2. Excellent. Very good. Now, they both lose 2 when they react, but Pi has more protons than Zapper. So where should Zapper go? It's going to go in group 2. Pi has more protons than Zapper. It's not 2, 5. 2, 5 would be Pi. I want to know where Zapper goes. So Zapper is going to go right here because it has fewer protons than Zapper or than Pi. And then finally, we have Pi at the end. And with that, our periodic table is complete. But our job's not done. Yeah, that's okay. I may have said it wrong. Sometimes these names throw me a little bit. Our work isn't done though, because they can still say to us, we want 20 kilos of Ernst, and that doesn't mean anything to us. So our next step now is to compare that to our periodic table to match their elements with our elements. All right, so we're going to go in this order right here. First, that's the PF. What element on our periodic table is first? Hydrogen. That's it. It is hydrogen. What about Bombal? Bombal is helium right there. B-O-H-E. Bombal is helium. What about Chao? Chao is lithium. What about Dogon? Dogon is beryllium. What about Ernst? Ernst is boron. Very good. The top of the boron group, right? This is the boron group right here. And this is their E right there matches our boron right there. All right, Floxit. Floxit is carbon. What about Goldie? Goldie is nitrogen. What about Nuyut? Nuyut is oxygen. So remember, we said that Nuyut is found as a diatomic molecule. Our oxygen is the same way. We don't find oxygen as an individual atom out in nature. We can create it. We can separate it from the other oxygen. Remember, we talked about ways to separate it last time. We can run electricity through it. We can raise it to high temperatures. There's ways we can break them. But in nature, they stay bonded to each other. They both have, well, how many atoms, how many electrons are in the outer energy shell of oxygen? Six, right? So by sharing 2, they are both happy, right? They share each other. They stay bonded together. All right, what about Apstrom? What is Apstrom? Apstrom is fluorine. Very good. Logon? Logon is going to be a noble gas. It is neon. All right, up here now. Bayou. Bayou is sodium and Zapper. Magnesium. Hi-ho. Aluminum. What about Sorry, I went too fast. Hi-ho is I'm going behind. Hi-ho is silicon. What about magnificon? Magnificon is phosphorus. You guys see what we're doing? We're just matching them up to the ones that are on our periodic table. So what about Oz? Sulfur. And what's next? Crat. Crat is going to be chlorine. And what about gypsum? Argon. Quaxel. Potassium. Doadir. Calcium. Rat trap. Gallium. What about tereblum? Tereblum, not arsenic. Yeah, germanium. So let's find tereblum right here. When we come over here, it is germanium. Arsenic is the next one. So that would be cissus is going to be arsenic. Yeah. What about volcania? I'm sorry, ERP. Skipped one. ERP. What is ERP? ERP is selenium. Volcania. Bromine. Wobble.
Krypton.
Krypton.
I didn't even know
Exalt.
this.
Exalt. Yeah, look at that. That is rubidium. Rubidium. Pi. Strontium. Anatom. Yep. Indium. And then Eldorado. Tin. And with that, we're done. We have now solved the puzzle. We've solved the mystery. We are able to enter into a trade agreement with these aliens because we know what elements on their periodic table match the elements on our periodic table. Excellent, excellent. Anybody have any questions? All right, so let's review. Remember, the first group except for helium, hydrogen, is called the alkali metal family. The next one are the alkaline earth family. Then we have all these transition metals in the middle. And then the first four are named for the element at the top: boron, carbon, nitrogen, oxygen. This one is a little different. It's not fluorine. It is the halogen family. And then finally, we have the noble gases on the end that do not want to react. We have the lanthanide series and the actinide series, which go right here. They're actually part of periods 7 and 8, 6 and 7 right here that go in that area there. All right. Good to know.
There are transition metals.
Yeah, the transition metals we'll get to. We'll talk a little bit more about them. You might have gotten there already. The aliens don't have iron or gold or silver. You're right. They do not.
And they don't have ultra heavy non-part of the families that on the periodic table over
Nope.
here, it's
No.
labeled white from, and then
Right. If we
carbon
go back
halogens-
here, yeah, they didn't have anything heavier than tin.
We
tin
don't
was
have
heavy.
the U, double U's.
Right, right. So let me pull back here to, yeah. So they have as far as 10. Where's 10? Right here. They don't have anything heavier than 50. 50 protons is the most that they have on their periodic table. But it helps us to be able to trade with them. All right. Did I play this for you guys already? I don't think I did. All right. So in one of your lessons, there's a video of a song that covers all the elements in the periodic table. And Daniel Radcliffe, who is the actor who plays Harry Potter, was on a talk show about 12 years ago. And he sang another version of the periodic table of elements. Yeah, it is Harry Potter. Now, he sings really fast, but I think it's pretty fun. So let's listen to Daniel Radcliffe sing the periodic table song. Vida. Did you have something to say? No? Okay. All right. Let's listen to Harry Potter sing the elements.
There's antimony, arsenic, aluminum, selenium, and hydrogen, and oxygen, and nitrogen, and uranium, and nickel, neodymium, neptunium, germanium, and iron, americium, ruthenium, uranium, europium, zirconium, lutetium, vanadium, and anthium, and osmium, and acetine, and radium, and golden, protactinium, and indium, and gallium, and iodine, and thorium, and thulium, and thallium. There's yttrium, and terbium, actinium, rubidium, and boron, gadolinium, and niobium, iridium, and strontium, and silicon, silver, and barium, bismuth, bromine, lithium, beryllium, and barium. And let's start the next verse. There's holmium and helium. There's holmium and helium and apium and erbium, phosphorus and francine and fluorine and terbium, and manganese and mercury, molybdenum, magnesium, dysprosium and scandium and cerium and cesium. There's lead, praseodymium, platinum, plutonium, palladium, promethium, potassium, polonium, and tantalum, technetium, titanium, tellurium, and cadmium, and calcium, chromium, and curium. There's sulfur, californium, and fermium, berkelium, and also mendelevium, arseninium, nobelium, and argon, radon, neon, and argon. Hold on, quiet. There's sulfur, californium, and fermium, berkelium, and also mendelevium, arseninium, nobelium, and argon, radon, neon, krypton, xenon, zinc, and rhodium, and chlorine, carbon, cobalt, copper, tungsten, tin, and sodium. Now,
Pretty fun. All right. So, any of you guys want some extra credit? If you learn any version of the periodic table of elements songs and can sing it in one of our live classes, you will get 25 extra credit points. Plus, you get serious bragging rights. I know the whole periodic table. That's pretty cool. What you have to do is send me a Canvas inbox message letting me know that you want to sing it in class, and I'll make sure to give you the time. Yep, you have to sing it in front of everyone. Yep. Can I use sheet music? Well, you can't have the words in front of you. So you have to actually memorize the names of the periodic table. Josiah, I'm not surprised. You've already memorized most of it. It's pretty cool to know. Excellent. All right. It is a lot of extra credit. Yeah, you have to work hard for those 25 points, but I think all of you guys can do it. Yeah, I can send the song to you. Sure.
Can I ask something?
What, Arhan?
I want to try it next class.
Well, let you learn it first. When you're ready, then you tell me.
Okay.
Okay. All right. So last week I sent you guys that interactive periodic table. I think it's pretty fun because it shows you what some of the elements are used for. This is another one that has a lot of really good information about the periodic table. So I'm going to pull this in and show you guys what this looks like. Hold on. This periodic table. Sorry, my link is not working. All right. Here we go. Now this one's pretty cool. It's got some really interesting things in it. If you look over here, so let's pick carbon. So you can look here and see carbon is orange. That means it is a non-metal. Match it up over here. The classification is non-metal. Let's look at the melting point of carbon. So we can see right there, it's this purple color right in here. The purple color is actually not even listed on this. I wonder why. The radius of an atom on this one, pretty small. It's going to have a small radius. The state of matter, it's gray, so it's solid. Carbon is solid, and this state of matter is going to be at room temperature. So it is solid. The boiling point of carbon is, again, it's this purple color right here. Not the darkest purple, but the next one. So the boiling point of carbon is going to be between 3 and 3.9 Celsius. The outer orbital right here is going to be what's called the p orbital. That'll mean something more when we get to talking more about orbitals in one of the lessons. And then how abundant is it? Well, look here. It is this orange color right here. That would be this one right here. And there are 1 to 9.9 parts per million of carbon on the planet. So taking a look at this, what is one of the most common ones right here in the universe? Not on Earth, but in the universe.
Why do not all of them show up? Like in size of atoms, the bottom one don't show up.
Yeah, those are probably not calculated yet. No data.
What?
Yeah. You know, it's kind of hard to measure size of something that really tiny. But this is pretty cool. I think this is a fun thing to play around with. So you can do it with any
Periodic table
elements.
sound isn't explored.
What element? What Evan?
The seventh row is not explored
Yeah, you're right.
yet,
You're right. It is not.
especially the gray parts.
Yep. Yep. And
What
this
are
one,
they even called?
yeah, it's exactly true. So there's no data. Now that could be that it hasn't been released, that somebody in some lab somewhere knows. But what's the most abundant one?
Secret.
When we look here at abundance, what is the most abundant element?
Hydrogen.
Hydrogen. What is the next most abundant? Josiah.
Helium.
Helium. And then what's after it? Ella.
Oxygen.
Oxygen. Very good. Very good. Now, one thing that's interesting when we look at states of matter right here, liquid right here. What are the ones that are found in nature that are liquid? There's only two. Isn't that interesting, Josiah?
There's mercury, and then there's bromine.
Exactly. So mercury is
What
Hg. This is bromine right here. Those are the only two of all these elements that are found in a liquid state in nature. That's pretty
What
interesting.
does sulfuric mean?
What does what?
Sulfuric mean. The green.
Oh, synthetic.
Yes.
Synthetic means it's made in a lab. Yeah.
And you
made
can't
in a
find
laboratory.
it in nature.
Those are
Never,
not found.
ever,
They're either
ever.
not found in nature or they're found in such tiny amounts that they're almost insignificant. All right. Anybody have any questions about the periodic table? Go ahead, Josiah.
If we memorize both songs and do both of them, do we get 50?
No,
Oh.
just one. That's too many points. How about this? If you memorize both, I'll give you 5 extra ones. You get 30. All right. So instead of 25, you're going to get 30. Oh, you overachievers, you. I love it. Matthew.
If I learn the really fast one and dress up as Harry Potter, do we get extra credit points?
You'll get bigger bragging rights. That's good. Do you have a Harry Potter costume?
Yeah, especially
Yeah.
when it gets colder. For some reason, my hair turns a darker color. Don't understand why, but then it works out for Halloween because it means I look almost identical to Harry Potter.
Yep, that's true. I went to a costume party one time dressed as McGonagall. I'm a big Harry Potter fan, so I'll get my picture of me in the costume and I'll show it to you next time. Yeah. All right, we're going to be done for the day. Anybody have any questions? All right, the reason that we learn this periodic table, the reason we spend so much time is that it is what's happening in that outer valence electron level that makes elements react with other elements and form all the things in the world. Like we wouldn't have all these things if they all had 8. If all of them were, well, there are some noble gases that do form bonds, make bonds with other elements, but they're in general, they don't like to. So if all of the elements that we had all had 8 valence electrons, we wouldn't have what we have in the world. It's because of that wanting to either gain or lose valence electrons that things bond with other elements and give us the compounds that make up our world. It's pretty cool and pretty important. All right. Great job, everybody. You solved the puzzle. Now go learn the song. All right. I'll see you next week. Bye.